Hey all, today we are learning Geometry 10.5 tangents. You guys will be able to use properties of tangents and can solve problems involving circumscribed polygons. So a quick reminder what circumscribed is. Circumscribed is when you have a shape outside of a circle. So for instance, this is not a polygon, it's a triangle, but it is circumscribed around that circle. Inscribed is when we have our triangle inside of our circle. So these are different things. We have different properties with each of them. And today we're specifically looking at circumscribed polygons. So we have some vocab here. A tangent is a line in the same plane as a circle that intersects the circle in exactly one point, called the point of tangency. Line AB is tangent to circle C at point A. Segment AB and ray AB are also called tangents. Now, guys, this is a different type of tangent from our trig tangent. I've actually never looked it up. Maybe they're related somehow. It's a little bit weird that we have the same vocab word that means something different. This sort of tangent is where you just have a line that touches your circle at one point specifically. It cannot touch at more than one. So a common tangent is a line, right, or segment that is tangent to two circles in the same plane. In each figure below, line L is a common tangent of circle F and of circle G. So line L touches circle F here, touches circle G there, or if the circles already only touch at one spot, you can put your line of tangent or your tangent line through there and create your point of tangency. So we have some examples here. It wants us to draw common tangents. If no common tangent exists, state no common tangent. So for this first one, there actually is no common tangent. If you only touched this circle at one spot, well, you couldn't cross into the circle. It's not like tangents work like this and then you can just stop. They have to go across the side. So like this would be a tangent, but it doesn't touch this one. Or this could be a tangent, but if we extended it both ways, it wouldn't be a tangent of the other circle. So there is no common tangent between these two circles. This next one, since these circles already cross at 2 points, to make a common tangent, we just have to lay our line across the side. You can go there, or you could go on the other side. There are some options. You guys try these two U-tries. There are multiple options here as well. Alright, so you can either, for this first one, lay a line across the sides. Hopefully draw a little better than I did. Or you can put it through the center, like this. This next one, you can also put it through the center, assuming those circles only touch at one point. Or you can also lay it along the side, like so. So we have a new theorem here, theorem 10.10. In a plane, a line is tangent to a circle if and only if it is perpendicular to a radius drawn to the point of tangency. So, you have your point of tangency here, T. As long as you can draw a radius that drops down at 90, you know this is a tangent line. That means that we can do some Pythagorean theorem here because we have 90 degrees. So it says segment KL is a radius of circle K. Determine whether LM is tangent to circle K. Justify your answer. So if this is 90, then it is tangent. If it is not 90, this is not a good Pythagorean theorem problem, then it's not tangent. So let's do this. We take leg squared plus leg squared equals hypotenuse squared. So we have 400 plus 441 equals 841. And when we add 400 plus 441, we get 841. Since this checks out, this is a right triangle, meaning that that is 90 degrees, so that segment LM is tangent. So we'll write that out. Segment LM is tangent because segment KL and segment LM are perpendicular. And this is by the theorem that's just above, theorem 1010. All right, you guys try this, you try. Okay, so same idea. We know this is a radius. We are trying to check to make sure this is actually tangent and doesn't just sort of look like it and not be a tangent line. So to do that, we check to see if this is a right triangle. So 14 squared is 196. 16 squared is 256. 21 squared is 441. When we add these together, we get 452 is equal to 441, which is not true, which means this is not a right angle. So that is not actually a tangent line. It either doesn't touch the circle or it actually goes through the circle in two places, not just one. So segment YZ is not a tangent line because YZ and XY are not perpendicular. This is also by that theorem 1010. It's just kind of a counterexample of why it does not work. All right, on our next page, we're going to use a tangent to find missing values. So this is just going to be basically Pythagorean theorem. Some of these problems, though, are set up a little crazy like this one. Eventually, on your next test, there will be one like this, but it's not quite as crazy as what we have here. You'll see what I mean in a minute. So, for this problem, we know that this is tangent. This segment here is tangent, which means this has to be 90. And if we want to find the radius of the circle, we can do that because we can use Pythagorean theorem. So we have x squared plus 24 squared. And here's where it gets weird. We need to equal this to the hypotenuse squared. We don't know the hypotenuse as a number or as a variable. We know it as x plus 16 squared. So we're going to bring back some stuff from Algebra 1. We should recall that if you have this little 2 here, you have to write those factors twice. So we have x plus 16 times x plus 16. And then we're going to FOIL these. Remember, FOIL means multiply your first two things, x squared, then your outside two things, plus 16x, then your inside two things, plus 16x, and then your last two things, plus 256. Now, I'm going to combine like terms, but I'm going to move it over here, so that way it's part of my problem again. I have x squared plus 32x plus 256, and then I'm going to bring down this stuff, x squared plus 576. Now, this is the problem that I need to solve. Everything else was just work to get here. And actually, this doesn't end up too bad. I am going to subtract x squared on both sides. They both cancel out. And then I'm going to subtract 256 on both sides. Now these don't cancel out, but they leave me with a fairly simple problem to solve. I get 320 is equal to 32x. So I divide by 32 on both sides, and x is 10. Which means that our radius is 10. So that is a fairly tricky problem, but we just brought in some things from Algebra 1. See if you guys can do basically the same problem on the U-try. All right, let's do it. We know that segment IK is tangent, which means that we have 90 degrees here, which means this whole side is our hypotenuse. So we're going to set it up basically the same as the last time. We have leg squared, so x squared, plus 16 squared equals x plus 8 squared. And I know that has to be on this side of the equals by itself because it's across from the 90. Same as last time, since we have this little 2, we're going to write that factor out twice, and then we are going to FOIL. Remember, FOIL is just an acronym. It stands for first, outside, inside, last. Then I'm going to bring it back over and combine like terms at the same time. So I have x squared plus 16x plus 64. Bring this stuff down. X squared plus 256. Now our solving is not too bad. Remember, I'm looking at just this now. I can subtract x squared on both sides, and this makes it easy because these cancel out. I don't have to do any quadratic solving or factoring or anything like that. Now I'm going to subtract 64 on both sides. This gives me 192 equals 16x. Divide by 16 on both sides. So x is 12, which means our radius is 12 if it asked us for more than just what x is. Okay. Next theorem, we have 10.11. If two segments from the same exterior points are tangent to a circle, then they are congruent. So if you have two tangents, so these only touch the circle at one place each, that go to the same exterior point, you are guaranteed that these segments are congruent. Once again, eventually when we have a test, there will be one question like this. So make sure you know how to do these as well. So we have segment AC and BC are tangent to circle Z, so they're only touching the circle at one single point, and they go and touch the same exterior point C, which means these have to be congruent. Now, I don't think this picture is drawn the greatest. It doesn't really look like to me that points A and B are tangent, actually, but just go based on what they're saying, okay? So since it says those are tangent segments and they intersect at point C outside the circle, these segments are congruent. And when things are congruent, you simply set them equal. So this solving shouldn't be too bad. I'm going to add 3 to both sides and subtract 3x on both sides. So I get that x is 5, and that's all it asks for. On the next page, there's a U-try of this. Go ahead and try it. Okay, so once again, it says these segments are tangent. I don't know if I believe that really based on the picture, but since it says it is, we're just going to solve like they are. They intersect at the same exterior point, which means these tangent segments have to be congruent to each other. So I'm going to set these equal. And then I'm just going to solve. So I'm going to add 17 to both sides. And I'm also going to subtract 5x on both sides. So we get 21 is equal to 3x. So x is equal to 7. Okay, and then we have one more example that kind of goes along with this. The round cookies are marketed in a triangular package to pique the customer's interest. In triangle QRS, circumscribed about circle T, find the perimeter of that triangle. So, once again, before we get started, there will be one like this on your test as well. Your test isn't for a while, but just giving you a heads up. We can figure this stuff out. Remember, if these are all tangent, which they are because it is circumscribed about the circle, that means it has to be tangent. We know, since this comes to point S here, these two segments have to be the same. So they are congruent in both 10. I know since this segment is 2, this one also has to be 2. It's kind of hard to tell which one it's talking about. They're both 2. This is our tricky part over here. We need to figure out what these are. And it's actually not too bad, since we know that this part is 2 and the overall here is 8. We don't want to just move the 8 over. That's not necessarily true. We want to take 8 minus 2, which is 6, and that tells us that this part down here has to be 6 units. And then, since once again this is tangent, this segment over here has to be congruent to that. And then, make sure you do not double count things. Like, don't count this 8 if you're going to count the 2 and the 6. Just count the individual pieces. Basically, just don't double count. So, I'm going to go through. I'm going to do 10 plus 2 plus 2 plus 6 plus 6 plus 10. That is what I am going to add together, making sure I don't double count. If you notice, guys, I have pairs. I have 2 10s, 2 2s, and 2 6s. So when I add this together, I get that the perimeter for my triangle is 36 centimeters, because it is in centimeters. Okay, you guys try the you try. Same idea. So it says a bouncy ball is marketed in a triangular package to pique the consumer's interest. If triangle ABC is circumscribed about circle G, find the perimeter of triangle ABC. So once again, I know some things. I know these two segments have to be congruent, so this is 12. I know these two segments have to be congruent, so this is 6. Since the whole thing is 16 and that partial is 6, I'm going to subtract them, giving me that this piece is 10, and this piece is 10, and then I'm going to ignore this one, and I'm going to go through and I'm going to add 10 plus 12 plus 12 plus 6 plus 6 plus 10. That'll guarantee I did not double count anything. And when I do this addition, I get that my perimeter is 56 centimeters. So we used our newest theorem there to figure out the perimeter of these triangles. Alright guys, that is all for today. You can flip the page if you have extra time and work on the 10.5 worksheet. Have a great day.